Hello, everybody, and I'm hoping you enjoyed your break. Today we'll start chapter 2, which is about convective mass transfer. Convective mass transfer, similar to convective heat transfer. So you have studied heat transfer, and they spoke to you about convection. So it is similar idea. So when we have mass transfer and the bulk is very important. And as you can see, the subtitle for this chapter is mass transfer coefficients. So we are dealing with MTC, the mass transfer coefficients in this chapter. So the objectives are two: explaining the concept of mass transfer coefficient for turbulent diffusion. So basically, I'm supposed to explain to you the MTC, but for turbulent diffusion, and you can now relate the convection term. Second thing is to define and use a special mass transfer coefficient for diffusion of A by analogy with molecular diffusion through stagnant B. In the previous chapter, I explained to you two cases. One of them was we have molecular diffusion and in which A is moving, B is standstill. That means it's stagnant. So I'm going to also use this ideal case in our lesson today. So mass transfer by convection. Mass transfer by convection involves transport of material between a boundary surface and a moving fluid. You have taken a fluid mechanics ended in the pipe when there is a fluid which is moving, and near the surface there was a kind of boundary surface. So it is similar. So you can imagine it that you have fluid which is flowing, and on the surface which is in contact with it, there is a kind of an area that we call it the boundary surface or the boundary area. This mode of transfer depends both on the transport properties. So transport properties of the fluid, examples are density, viscosities, etc. And on the dynamic characteristics of the flowing fluid. That means its velocity, for example. So this is a kind of dynamic characteristics of the fluid. So that's that. So when a fluid flows past a solid surface under conditions such that turbulence prevails. Now we are telling that if the fluid is moving, we have the case that there is turbulence. Turbulence is created, so that means quite fast. There is a region close to the surface where the fluid is predominantly laminar. So although the fluid itself is flowing turbulently, in the area which is next to the surface, the behavior is laminar, although inside the bulk it is turbulent. And the particles of the fluid immediately adjacent to the boundary of the solids are at rest. We also, the fluid mechanics, we say the velocity is zero next to the surface of the pipe, for example. It is similar approach. So we are telling that the area next to the surface is laminar, and it's controlled by, in that case, by diffusion. So molecular diffusion, in that case, is responsible for mass transfer through the stagnant and laminar flowing fluid layers. And this is what we said in chapter 1. Chapter 1, we stated that if it is stagnant, not moving, laminar, then the controlling mechanism is the molecular diffusion. The controlling resistance to convective mass transfer is often the result of this film of the fluid. Now, we know that there are two types. We know that there is molecular diffusion and there is convective mass transfer. Convective because of the turbulent, and the area next to the surface was the molecular diffusion. However, who's controlling? Who's controlling the mass transfer? Well, the controlling of the mass transfer is the film of the fluid, is the layer of the fluid next to the surface. I hope this is very clear for you. This is the reason I put it as a red, because it's important you understand that there is a resistance in the bulk and there is a resistance in the film, but the one which is controlling is the one which is the molecular diffusion. This is the reason we studied whole chapter about molecular diffusion. Although as chemical engineers, we prefer the convective mass transfer because we want everything to be done fast. So, however, under most convective conditions, this film is extremely thin and its thickness is virtually impossible to measure or predict theoretically. Yani, as if I ask you go and measure for me the thickness of a film, which is hypothetical film, then you will never able to do that. Therefore, we cannot use any equation that there is a film thickness in it. So as engineers, we prefer something else. We prefer the mass transfer, the mass transfer to be controlled, and we should have the coefficient. So the mass transfer coefficient rather than the thickness, we will be using it. With increasing distance from the surface, the character of the flow gradually changed, becoming increasingly turbulent. This is expected. In the turbulent region, particles of the fluid no longer flow in ordinarily organized way, similar to the laminar. Instead, large proportion of the fluid will have eddies. Eddies يعني بالعربي دوامات move rapidly from one position to another. So that's the turbulence and the eddies. These eddies contribute considerably to the mass transfer process. Because the eddy motion is rapid, mass transfer in the turbulent region is much more rapid than it would be under laminar flow. This situation cannot be modeled in terms of fixed law. So we cannot do the fixed law that we have used it initially. So we are going to be explaining it in terms of mass transfer coefficient, which is basically an intelligent way that engineers manage to explain this situation. So the mechanism of the flow process involving the movement of the eddies in the turbulent region is not thoroughly understood. On the other hand, the mechanism of molecular diffusion, at least for gases, is fairly well known, since it can be described in terms of kinetic theory to give results which agree well with experience. I explained to you all of this. What is written on this slide, it has been already explained to you. So when we explain the mechanism of molecular diffusion, we spoke about gases and liquids. Then we said that for gases, we can predict well the diffusion coefficient, etc. Easily because we are using the ideal cases, the kinetic theory, and we took the assumptions. So that has been covered. Now, what we are telling is that that mechanism is well understood, but the mechanism for the turbulent is not thoroughly understood. So what to do? Therefore, it is natural to attempt to describe the rate of mass transfer through the various regions from surface to the turbulent zone in the same manner it is found useful for the molecular diffusion. So the one which has been explained to you, you naturally wanted to be used for further discussion. So there were two situations in chapter 1, equimolar counter diffusion and diffusion of A through stagnant B. And these were defined by the equation in the form that flux is proportional to the concentration difference. We remove the proportionality, we put equal sign. So we have a kind of coefficient that was the constant. Since concentration may be defined in a number of ways, that the standards have not been established, a variety of coefficients were defined. So this coefficients in the flux, we defined a few of them, and we'll see it today as well. So let's have a look. So if we take the case that there is diffusion of A through a stagnant B, then we can say that the flux is proportional to the driving force. Our driving force in terms of the mole fraction. So for gases it's Y, and for liquids it's X. And we know that there is this driving force was in terms of length. So flux is equal to mass transfer coefficient, and mass transfer coefficient is basically the capital F G, because it's for gases, and we multiply by driving force, that was the length term, 1 minus YA2 over 1 minus YA1. And for the liquid, same thing, but instead of Fg, we'll put Fl, and that will be our mass transfer coefficient. You know that F basically is CdAb over the film thickness, the delta. So that's that. Another thing we should be careful about, this is correct when it was dilute concentration, and it is not concentrated solution. If it is dilute, then we are using the F. So if we want it to become more concentrated, then we have to use the small k. So that means the mass transfer coefficient. So we can now rewrite the equation in terms of flux. So Na as a flux is equal to Fg over Ybm multiplied by the change in mole fraction. What is Ybm? B, so you know it is for binary, so A and B, so that's your B, and M is the mixture. So Ybm, if you look at the third equation, Ybm is equal to Yb2 minus Yb1 divided by the length term. So that's how the Ybm is defined, because you are opening the derivative and you have to find the Ybm. Now, if you go back to the first equation, this will be equal, the flux will be equal to mass transfer coefficient Ky multiplied by the change in mole fraction. So mole fraction stays as the same. However, Ky now is equal to Fg over Ybm. So Fg, which is mass transfer coefficient, and Ky is again mass transfer coefficient, but they are different. One of them for the dilute, another one is for the concentrate. So in the last equation, it is explained to you the value of Ky is equal to Fg over Ybm. Same thing for the liquid, Na is equal to Fl, mass transfer coefficient in the liquid, divided by Xbm, and Xbm is again defined for you as equal to xb2 minus xb1 divided by the length. And also, when you substitute the FL over xbm, it should be equal to mass transfer coefficient kx. So that's that. Since concentration may be defined in a number of equivalent ways, other definitions also of mass transfer coefficients, for this case, we can use it. Yeah, for example, the mass transfer coefficient Na is equal to Kg multiplied by Pa1 minus Pa2, because our driving force is change in partial pressure. So partial pressure Pa1 minus Pa2 multiplied by the mass transfer coefficient Kg, small kg. If you have the concentration, then it is Ca1 minus Ca2 multiplied by Kc. If you have also this for the liquid, then it is Cal minus Ca2. So Ca1, sorry, minus Ca2. So that's Kl for the liquid. Fl, now we can tell it is equal to Kl multiplied by xbm multiplied by C. This is the definition of Fl, and that's equal to Kx xbm. Now you can see from this equation the relationship between Kx and Kl. Okay, so you can write down Kx is equal to Kl multiplied by total concentration. Fg again is equal to Kg multiplied by Pbm, and that's equal to Kc Pbm divided by RT, etc. So these slides show you relationship between mass transfer coefficients. We have different mass transfer coefficients because we are having different driving forces. So based on that, we have to choose the proper way. Notice that in the case of diffusion of A through stagnant B, there is a bulk motion contribution to the total flux. Yeah, and this bulk motion, we showed it because it was in log form. So when we had the length, that means that we have the bulk. For that reason, the newly defined K-type mass transfer coefficients are non-constant, but usually depend on the concentration driving forces. So based on the, as we just mentioned, different concentration driving force, different K values, and they are not equal. For every dilute solution, the bulk motion contribution is negligible, and the driving forces become approximately linear. So here we are assuming that if it is dilute, then the driving force will be linear. In mathematical form, this follows the fact that for dilute solution, Ybm is equal to Xbm is equal to 1, because the B will approach to 0. So we'll take two examples now, and hopefully we'll try to apply these equations. So the first example is telling you blood oxygenator are used to replace the human lungs during open heart surgery. If you have an open heart surgery, then there is a kind of oxygenators are replacing the lungs. To improve the oxygenator design, you are studying mass transfer of oxygen in the water at 310 Kelvin in one specific blood oxygenator. So you are dealing with mass transfer of oxygen into the water, and the temperature is given to you. From published correlation of mass transfer coefficient, you expect the coefficient based on oxygen concentration difference in the water is equal to 3.3 10 to the power minus 5 meter per second. So one thing here, you see the value, and it is to the power minus 5. And second thing, you should realize the unit from now on. So the unit is given to you, and each one of these mass transfer coefficients have different units. Calculate the corresponding mass transfer coefficient based on the mole fraction of oxygen in the liquid. So what he wants you to find? Find the MTC but based on the mole fraction of oxygen in the liquid. Try to solve it yourself before you continue the next slides. If you are not able, just proceed with this example. So, solution. First of all, we'll neglect the water evaporation. There is no evaporation of the water. And the liquid phase, this is the case of diffusion of A through stagnant B. So we have only one of the molecules moving, the other one is stagnant. So you have to make it very clear that this is the case. Second thing, you have to define what is A and what is B. So A is oxygen, the one which is moving, and B is the water which is stagnant. Second thing, since the solubility of oxygen and water is extremely low, we are dealing with dilute solution. You have to decide regarding concentration of your solution. So you know that oxygen is not soluble or it's very low solubility in the water. Otherwise, all the oxygen in the world goes into the oceans, correct? So we have to say that is we are dealing with dilute solution. So in that case, the use of K-type coefficient is fine, appropriate. From the information given, which is coefficient based on the oxygen concentration difference in the liquid and the water, KL, the value that was given to you is 3.3 × 10⁻⁻5 meter per second is the small KL. We know that Kx is equal to KLC. From where I got this, you have to go back to this equation, and you know from the FL is equal to KLXBM multiplied by C is equal to KXXBM. So make just a bit of algebra and you will find the same conclusion, that Kx is equal to KLC. Since we are dealing with very dilute solution, then you can find the Kx. Basically, it is 3.3 × 10⁻⁻5 multiplied by total concentration. Total concentration is the concentration of the water, because we said the solubility of oxygen in the water is very low. So how I reach 55.2? Well, try to get it from the units. This total concentration is kilomole per meter cube. So can you relate two variables so that you will manage to find concentration of water? And should be equal to 55.2. I will help you a little bit. Remember, the density is 1000 kilogram per meter cube, and from there try to get the kilomole per meter cube. So that's that. So you find the Kx, which is equal to 1.82 × 10⁻³ kilomole per meter square per second. So you can see now the unit of KL was meter per second, and the unit of the Kx is different. So he wants you to find the mass transfer coefficient based on the mole fraction of oxygen. So basically what he wants is Kx. So that's the first example. Second example, gas absorber is used to remove ammonia from air by scrubbing the gas mixture with water at 300 K and 1 atmosphere. I want you to make a kind of block or a square or rectangle, and in it there should be 2 inlets coming and 2 outlets going out. So inlet to the gas absorber is basically ammonia and air, and also water. So you have 2 inlets, one is coming from top to bottom, and the other one is going from bottom to top. you should realize the one coming from top to bottom should be the liquid. So if you do and make this drawing, and it should be at 300 K and 1 atmosphere, at a certain point in the absorber, the ammonia mole fraction and the bulk of the gas is 80%, while the corresponding interfacial ammonia gas phase is 0.73. So there is a kind of change in ammonia concentration or mole fraction from 80% to 73.2%. So that is a kind of driving force. The ammonia flux at that point is 4.3 10 to the power minus 4 kilomole per meter square per second. So that is the flux of ammonia. Neglecting the evaporation of water, calculate mass transfer coefficient in the gas phase at that point in the equipment. So based on this statement again, he wants you to find the mass transfer coefficient in the gas phase. I suggest you try to solve again from the slides. You have to find the proper equation and try to solve yourself. And after that, you check the answer. So if you are going to neglect the water evaporation, that means it is mass transfer or diffusion of A into stagnant B. So ammonia will be A and B will be the air. So you have to define first what is your A, what is your B. However, because of the high ammonia concentration, it was 80%, K-type coefficient should not be used. And instead, we are supposed to use the equation, there is the Fg. So since it's not dilute, okay, we are supposed to use the F, capital Fg. So the mass transfer coefficient that is asked in this example should be the F type, not the K type. So let's go back to the equation. This is the equation. Na is equal to Fg multiplied by ln 1 minus Ya2 divided by 1 minus A1. So he wants you to find the Fg. The flux was given to of the ammonia, which you called it A, and Ya2 and Ya1 for the ammonia also was given to you. So in that case, it's straightforward. But you should know that which one is which. So if you do that, the Fg will be equal to 1.47 10 to the power minus 4 kilomole per meter square per second. And that's the unit for the F mass transfer coefficient, F type. So you should be feeling comfortable with choosing which units to use for each one of them. Another thing, you should be feeling comfortable which equation to be used. So that's it for today. Have a good time.